Good evening, I'm Johnny Gabriel Masar, and I'll be explaining my work in Laboratory Activity 1, Plotting Analog Signals. So the objective of this activity is understanding how to generate and visualize analog signals using Python, applying NumPy for creating time domain samples of signals, use Matplotlib to plot sine, cosine, combine waveforms, analyze the characteristics of analog signals from their plots, which are amplitude, frequency, and phase. So the materials that would be needed is a computer installed with a Python, or you can use your Android phone with an application called FileDroid3. So the libraries that are mainly needed is NumPy, Matplotlib, and to be installed, it will be pip install NumPy Matplotlib. So let's start. This is the sample code that was given and the sample output. And our objective of the output should be a 5 Hz sine wave, a 10 Hz cosine wave, and a combined waveform superposition of two signals. So, so here's the code from the activity that is now plugged into the Python, which is PyCharm application. So let's start off. So what is the import and import NumPy? These are two libraries that can be downloaded from the library section here in Python. So what is t equals mp.arrange in the within the parentheses of 0, 1, 0.001. So 0 is actually the start, 1 is the stop, and 0.001 is the increment, or how fast it would generate. This increment is around 1 millisecond. So t represents 1 second of signal sampled at 1000 samples per second, which is 1 kilohertz sampling rate. Now, below that, we have sine wave. This is the sine wave. So let's start with this formula. So sine wave is equal to mp dot sin 2 times mp dot pi plus 1 f1 times t. So in this part, it is the equation which is equivalent to xt equals sine in the parentheses of 2 pi ft. f1 is equal to 5, where 5 is the frequency source. So we have 5 hertz, and f2 is 10 hertz. If we plug it in, it would be 2 times pi, which is 3.14 times 5 hertz times the time. This is the time itself. Same with the cosine wave. To add in also, the cosine wave has the same shape as the sine wave, but it starts at its maximum amplitude phase difference of 90 degrees. So plt.figure means plot figure with a fig size which is equal to 10 by 6. So this creates a new figure window for plotting with dimensions 10 inches wide and 6 inches tall. It ensures the plots are large and clear, especially when showing multiple subplots. Here are the other codes, the PLT dots from code line 17 to 21. PLT for code line 17, this divides the figure into 3 rows and 1 column of subplots and selects the first one of the sine wave. PLT.plot, which has a time sine wave inside the parentheses, plots the amplitude versus time. The title, X label, and Y label labels the graph for clarity. And the \n in the title inserts a line break, neatly adding your name, which is my name, the author of the code, for personalization. And the first graph visually shows the 5 Hz sine wave oscillates smoothly 5 times per second. It is the same with the cosine wave. What about the combined signal? Also, to add in, this R here means red. The G means green. This sine wave would be color blue. I think it's the default color for the first wave line. So within the combined sine wave, you combine the sine wave values and the cosine wave values. Same plotting where we simulate a composite signal, which is common in digital signal processing. The third subplot displays this green waveform G represented. Its shapes is more complex because it is a superposition of two different frequencies, 5 Hz and 10 Hz. Line 38 and 39 outputs the wave. And here is the final output. Thank you.